And so in our metric system, as you can see, the reason why we use, we don't put centimeters in our system here is you notice these are always powers of 3. So it makes a nice significant, it's an easy convert from one to the other. It's easy to change from one thing to the other. So not hard to do. And basically in this class we're going to use meters, maybe kilometers, and maybe millimeters. But that's about it. We don't use any of these extreme ones in this class. But every unit that we do in this class, all the way through power and energy and all that, can be based on the meter to kilogram a second. It's just different variations of those. All right, the next thing we want to talk about is something called significant figures. When you measure something in physics or anywhere, no matter what you do, no matter what you measure, anything you measure, you can only measure it as precise as your measuring system. And so if I'm trying to measure the size of like the book here, or let me measure my phone, and I want to see how big the phone is, using a meter stick, the most accurate I can get with the meter stick would be to the nearest millimeter. All right, now there's ways to measure it more accurate, but there's always a limit. There's always a limit to how accurate it is. And physicists, we have to worry about that. That's the biggest difference between mathematics and physics. Physics, we solve real-world problems, and so there's always a limit to how good your answer is. So for example, if you measure something, let's say I measure it to be 2,300 meters. Now, when I measured it, I'm the only one that knows how accurate that is. Is it accurate and it's rounded off to the nearest hundreds of meters, or the nearest tens of meters, or the nearest meter? We don't know that, but physicists use this significant figures as a way to say how accurate this was measured. Zeros, if they're to the left of the decimal point, remember the decimal point is implied here, those are just place value holders, and so they're not significant. So this 2,300 meters would have what we call two significant figures. How you determine it is you start at the decimal points, and you go left until you hit the first non-zero number, and then you count how many numbers there are. Let's do another example. Let's say I have this. How many significant figures does it have? Same thing, we're starting at a decimal point here, and we're counting over until we hit the first non-zero number. And so I go over, those don't count, and then I count from there, I got 1, 2, 3. So this has 3 significant figures. Yeah. Which is telling me how accurate that is. There's a good story about this. When the British were first measuring, they wanted to measure the height of the highest mountain on the earth, Mount Everest. And when they did it, they calculated to the nearest foot. And this was back in the late 1800s. And they came up with that it was exactly 29,000 feet high. But they didn't want to publish that it was 29,000 feet high, because then they would think that everybody would think that they only measured it to the nearest 1,000 feet, and it was rounded to that. So to make people know that they measured to the nearest foot, they actually published that it was 29,002 feet. Now we know that their number was actually off a little bit, and that where they measured from sea level wasn't quite right, and so it's actually 29,200 and some feet now. So that's just an explanation of why or how significant figures matter. Let's look at numbers that are less than 0. If we have like 0.00301 meters, how many significant figures? Well, it's the same thing when you go to the right instead of to the left, is you go from the decimal point until you hit the first non-zero number, and then you count from there. So I go 1, 2, those don't count, they're just place value, so I have 1, 2, 3 sig figs here. Now, do the same thing, but the only tricky thing is what if you have a number that goes from a positive past the decimal, so you have a number like this. Like what if I have 20.042, how many sig figs does that have? Well, if you have decimal points over here, you can't just go to here and count those two because these become significant. And so in this case, the whole thing is significant. This has 5 significant figures. Okay. All right. Why do we care about significant figures? Well, when you do a problem, you're going to have to add or subtract or divide or multiply or use a trig function or something. And maybe your answer, you started out with something that was 10.0 and 4.1, but your answer on your calculator says 2.397654, whatever. If you put all these down there, I'm going to tell you that your sig figs are wrong, and I will count off points. Why? Because you can't make an answer more accurate by just multiplying and dividing numbers. So if you only measure it to this accuracy, you can't have an answer that gets super accurate. You can never make the answer more accurate than what you started with. So what we would do here, if these were the inputs, this has 3 significant figures because there's that 0 there. Okay? If there was no 0, it would only have 1. But by putting the 0 there, that makes it have 3. This has 2. So this has 3 sig figs, this has 2 sig figs. You always go for the lowest amount of sig figs, and then you round your answer to that. So my answer would be 2.4, and I would ignore the rest of that. Remember, I rounded it up to the 2.4. Okay? So always look at in the problem, especially when you do the mastering physics, because they get picky about sig figs, look for which one has the significant sig figs. Now, I got to admit, the book gets very sloppy about this. Some things you don't worry about are if they give you an angle, and they say the angle is like 10 degrees, that means it's exactly 10 degrees. You ignore the sig figs for that. You look for something else in the problem to determine the sig figs. Angles are always exact, so they don't have any sig figs at all. And yeah, you just have to look at the problem. Different problems are different ways. And occasionally the book gets a little sloppy, which I don't like, but that's one of the few problems with the book. I know students get messed up with it. So the other thing, that big problem that I have students do, is something called round-off error. Because we're going to do problems that have many, many steps. And when you have many, many steps, if I have to say, oh, I have to take these numbers to get another number, and then I have to take that number and multiply by another number I derive to get the final answer. Don't round off your numbers in the intermediate steps. Because if you round them off, then when you get your final, it's not going to be right. You have to only round off at the end. I wait till I get the final answer, then I round it off. But the intermediate steps, don't round it off. Keep at least 2 more digits than your significant figure. So if I have 2 significant figures, my intermediate steps, I keep at least 4 sig figs. So that you don't end up with a round-off error. You don't end up with the wrong answer when you get to the end. Especially with mastering physics, because when they want 2.4, if you round it off early, you might get 2.3. They're going to count it wrong because it's not the right answer. So just be careful about that. All right. That's significant figures. I know a lot of people have not heard about that. They don't talk about that lots of times in high school or other levels. Some of them do. It depends on how good your high school physics class was.